Good morning and welcome everyone. Thank you for joining today's webinar. My name is Lisa Holmes and I'm the Marketing Director at Royal Circuit Solutions. Today we are discussing the ABCs of Flex PCBs. Now I'd like to go ahead and introduce our presenters. Our first presenter is Scott Kono. Scott is the President of Royal Circuit South. He has worked in the flex circuit board industry for more than 10 years. Scott will be joined first by Bob Meyer, who is the Vice President of Operations. Bob began his career as a process engineer for Speedy Circuits, where he spent 21 years learning the ins and outs of the circuit board industry. He joined Royal Circuits in 2016. And Scott and Bob are also joined by Victor Hemingway. Victor is Royal Circuits COO. He brings more than 40 years of experience helping manufacturers deliver high-quality products. So at this time, I'd like to go ahead and turn it over to Scott to get us started.
Okay, thank you, Lisa, and we'd like to thank and welcome all of the attendees today to our presentation on Flex and Rigid Flex. It is the ABCs, but we hope that we can bring a little bit of more of the basic Flex concepts and a little bit more of the advanced concepts that we're seeing out there. So there's something for everyone. First of all, our group, Royal Circuits, we're based in California. We are a quick-turn PCB specialist with about 130 employees, both in Northern California and Southern. Our Royal Circuits North, based in Hollister, specializes in rigid and HDI PCBs on a quick-turn basis. And our group, Royal Circuits South, in Southern California, Santa Fe Springs, we specialize in flex and rigid flex circuits. We've just moved into a brand new state-of-the-art building here in Santa Fe Springs, and our specialties include everything from quick turn to multi-layer flex, rigid flex, and assembly. So we cover the full gamut of the flex circuit industry. Some of our customers, we have it pretty spread out on the medical, mil-aero, consumer, and commercial. And in terms of flex circuits today, it certainly is a growing market across the board, so we're very excited about the prospects of the flex circuit industry. Today we're going to cover a basic overview of the flex options, tips on designing with flex circuits, some of the material considerations. We're going to cover some best practices, and then we'll close it with some rigid flex and high-speed technology that we're seeing to really round out our presentation of the flex and rigid flex industry here. First of all, we'll start with the basic of what is a flex circuit board. Really, today, flex circuits are a technology of connecting. It's an interconnect, very similar to a PCB. The difference, of course, is that it's very, very mechanically flexible, so we can bend it in many different shapes and forms. If the base material, we'll cover that today, is typically a polyimide, and we will cover that either with a cover coat or solder mask, and we're going to cover all of those elements today. Today in flex applications, we're seeing it very, very prevalent in the medical industry, in terms of aerospace, where we've got a customer that works in the night vision industry, telecommunication, radar, and in commercial. In the daily life, we see it all around us, the flex circuit today, especially in the wearables, from the Fitbit today to everything that we're seeing in the medical industry. And so it really is a growing industry, especially with the packaging and everything has to be lighter and tighter. We're seeing the flex circuits being utilized all over. And where the Fitbit was more measuring your pulse rate and number of steps you take, today the flex circuit has gotten to the highest level where it can actually monitor and diagnose a lot of the inside of the human anatomy in terms of the cells and types of cells that are going through the bloodstream. So it's a very exciting period that we're in terms of the advancement of flex circuits. The types of flex ranges from a single-sided to double-sided, multi-layer, sculptured flex. It's really pretty much unlimited in terms of our flex. We've seen new designs and new applications coming up all of the time. Today, we're going to go through some of the considerations in terms of the stack-ups, the materials used, the stress factor, finishes, cover lay, and so forth. In terms of the material considerations, we typically first take a look at the Kapton thickness, the adhesive-less construction, and the copper thickness. So those are some of the things that we take into consideration at the very beginning as we plan the journey of a flex circuit. Bob is going to cover a typical single layer flex stack-up, which shows here the basic
layout. We're going to go see in the next few slides some different configurations, but one on the screen right now is a basic single-sided flex, supported with, in this case, would be LFO 130, which is basically 1 mil adhesive, 3 mils of Kapton thickness. And then the LF is a pretty flexible material when it's single-sided. This stack-up is showing you some areas where we have 2 or 3 additional layers on there, and those are typically extra flex materials, Kaptons, and it's rigidizing or making stronger the flex area where a component might be. So you can, the stress points won't cause you to lose a part or lifting, that type of thing. So again, at the end down there in zone 4, they'll build up maybe where a connector goes together. So we'll try to hit a certain thickness. When we build the ZIF connector type boards, it's always around 12 mils thick in that area. So we use different cover lay combinations to achieve thicknesses and resistance there.
Yeah, so this example shows just a basic stiffener, which is we put LF 130 and 150 together to make a 10 mil thick stiffener in this case. Very common to have a very thick stiffener. And so this is just a basic single-sided flex. As far as the next one, which is a 2-layer flex.
Yeah, this is double-sided flex. This is probably the most common, where we're putting drilled and plated hole through there. We got a cover lay on the top and bottom. As we finish, we'll put a rigid stiffener at the very bottom. You can see a 31 core, and that'll be the general pack of where the components will go, or it's reinforcing for a stiffener that's going to be plugged in and out, so it doesn't interfere with the assembly to the part. On the far end in zone 2, you're looking at 2 pieces, what would be 220, so that makes that like an 8 mil stiffener, and that's typical of what you'd put on the end with the 1 mil material to achieve the right thickness for a ZIF connector. You'd be up around the 11.8 mils, 12 mils is the target, I guess, in that 3 millimeter range. So, yeah. And that's a pretty common thing. If you look at the layout, it has a 1 mil core with the 2 1-ounce copper layers. So, flex manufacturing, we occasionally will make our own material. We'll apply a rolled annealed foil to the base Kapton. We buy the material already attached. There's an adhesive material that we purchased that has no acrylic in it, and they all serve a different purpose. Next, going into our lens drill equipment that we use here, it's the most important thing about this equipment is it's all visual and fiducial recognition. We can do controlled depth drilling. We align to surface targets to help get better registration for your routing and secondary tooling and those type of things. Basic laminator, we use photoresist dry film to put the images on to protect parts when we're doing plating processes. This is our direct imager. Probably 95% of the imaging we do is on this machine. It's taking your data and it's doing a one-off direct image on every panel. It makes it more accurate, and it fits the panels to movement and other registration factors. We run a print and etch system with a cube prick etcher. That's what we're looking at here. It's pretty typical of in the industry. Handling is always an issue on the very thin flexes. We run down as thin as a 0.5 mil on some of our Kapton. We use leaders and sometimes frames through the machines to prevent the real thin materials from getting stuck or bound up. This is a picture of our layup area where we'll be putting the cover lays and building the substrates and also laying up the components for the flex. Lamination, we have a series of different presses, different sizes. One thing in flex is there's a lot of small pressing and pre-tacking, so we need some multiple capacity to get the products turned quickly. So we're currently running ESI lasers, the 5200 series. We have 6 stations we have set up in our shop, and they each do some things better than others, but they all overlap into routing, drilling, depth drilling, and we have a lot of resources to be to move for different jobs. Just the consideration with flex, the biggest driver will be where you're going to use it. What we call is our static applications, which generally is going to be installed once, but they want to bend around other parts. Maybe it has to, make a right turn and plug into a connector, those type of things. But generally a one-time bend to fit in a box or an assembly. Semi-static will be ones that move a little bit when, calibrating, maybe moving to another spot in the system, but it's not moving constantly. And then the final one is the dynamic bending, which you'd see on a printer or something to that effect. That's going to be constantly moving back and forth. Test heads, things of that nature, probe tests and things. And then final bend radius is always important when you're considering how thick to make the flex. That's a basic chart of where we're at on the single double-sided with a 10x overall thickness for the bend. And then when you get down to the multi-layered flexes, they're going to be less flexible just with the total thickness, and again, they'll have a little less of a bend radius. Things they do in design to help bending would be looking at a solid plane, going to a cross hatch, which is much more flexible because you're pulling out copper out of the whole build. So things we'll look at there. Little instruction on layout. If you look at the picture to the left, what we call staggered conductors, that's preferred when you lay out. If you tend to stack them on front and back, it creates a high and low pressure area and pressing, and then takes a lot more force or a lot more adhesive that to fill those type of areas. When you're filling those areas, you also going to be squeezing onto your pads and areas that you want open. Picture on the right is just a few examples of what the trace width, the areas that you'll clear out for cover lay, avoiding bending. You got to know where you're going to bend the board, so you may not want to reduce traces there, keep them a little heavier. That all helps in the reliability of the part. We talked about this a little early, ZIF connectors, which is one of the more common, designs that go on the end of the parts. And there's a couple examples. There's a stack up to the right, and we see that probably the most common stiffener on part. I should say connector on parts.
And again, the thickness.
The thickness is right about 3 millimeters, right at 11.8 mils, 12 mils, plus or minus 1 or 2. And we have a lot of different material combinations to get to that number. Example of some stiffeners that we put on the picture to the center. It's got stiffeners in the 2 parts in the center, then to the left and the right wing. Up on the right, there's a combination. On the far right of that picture, there's a rigid stiffener. It's FR4 material. And then right below it is the Kapton stiffener, which is a little thinner for a connector. Down below on the lower right is a rigid flex with the non-bonded flexes, and then they have stiffeners in different areas on there. So this is a picture of a large board. We're doing a second cover lay, we call it, on there. But instead of having another actual flex layer, they have a silver shield that they're using for a ground, and that helps keep the board thinner. So typically we would put a cover lay on, screen the silver on, very thin, maybe about 1 mil thick, and then come right back and put another cover lay on. So this gives you the isolation over your traces and things that a lot of times they'll have openings in most cases to the ground connection, so that silver will actually be connected through a opening on the first cover lay, and then it gets sealed up with the second cover lay. Solder mask is very common, a flexible solder mask. If you're not using a dynamic bend, then the mask is pretty good. It's a faster way to define the layer. You don't have to go through a lamination cycle. We see a lot where we'll put the capped on cover lays where you're going to bend it. And then in the area where we're doing assembly, where you might have some tight pitches and some BGAs, we'll put the solder mask just in the areas where you're doing assembly. And then that's generally reinforced with a stiffener behind it. So you won't actually be flexing the mask. But that's actually a very good build to use the two together when you get real tight features. Some of the finishes that we use, we see a little of everything, but Enig's probably the most popular, followed by hot air solder level. And then there's a mix of the rest, depending if you're doing any wire bonding, you might see Unipeg. We do some electrolytic hard gold tips and contacts, but that's kind of very seldom anymore. Immersion tin for the quick assembly, a lot of the commercial products will use that. And then we'll use pure tin for the Rojas products as well. So again, just some more of the recommended finishes you can see. We do like that round board in the middle is an N-Tech finish where it's just actually copper, and that's something that they're going to be hand soldering more than likely parts onto. So that's just keeping the copper clean from oxidizing prior to finish. On upper right is a small flex part that's Enig with the contacts, and then the chip carrier there is the Unipeg finish, which is pretty typical. And then the hard gold sometimes will have, there's a few demands where the contacts are, like on this particular board, there's a series of buttons that go over the top of that with the, and they'll sometimes be a hard gold, but typically what we see anymore is that they just use the nickel underneath and the gold's just keeping it from oxidizing. So Enig's usually fine. Scott can explain more of this product.
You know, in the 1990s, the flex used to be a typical standard single-sided flex is something that we used to do for one of our customers, where it was, as Bob had mentioned, it's a Kapton flex rigidizer here, and then we got an FR4 here, and basically it was two LEDs, a green and a red LED on both sides, and a beeper in the middle, an audio, and this is the connector. It would go into one of these guns that you see at Walmart and so forth, and that was our typical flex circuit. For us, everything changed around 2009, where the iPhone 3 introduction of that really created the need for speed packaging, everything from Wi-Fi to the various GPS technology that translated to all across the board, medical, military, and that really created the need for a lot of the new rigid flex and the need for speed. So there, in terms of the board-to-board connection, where it used to be hand soldering wires to jumper wires between board-to-board, rigid flex has become the most efficient way for that, and also for a lot of the connectors that are going on. But in terms of packaging, there really the packaging is like there's nothing that can compare it, because you can really just fold it into a small little minute space, and that's really the number one issue that's driving a lot of the rigid flex today. A typical rigid flex stack up here. Maybe Bob, you could talk about this.
Yeah, this is a higher 8-layer rigid flex, where it's typically we have two flex layers in the middle. They're bonded together. If you look in the very middle, they call an LFO 212. So those flexes would be bonded. We only put the flex and the acrylic in the areas that are going to bend, the flex materials and the cover lay. The AP material, which has no adhesive, that goes throughout the board, and then we bond that with a no-flow prepreg, which is the 67N Hitachi material that we use. It's a low flow that keeps it out of the pockets. Now the cap layers on this particular one are a polyamide, and that's pretty typical of a build that we would do as a rigid flex, fairly balanced. This particular one showing 2 drill cycles, so it would have an epoxy fill via and then a final drill in the same buildup. And then this is that actual board finished. So it has a BGA and a couple other samples connectors. The wing arms are rigid flex, and they bend down to plug in the connectors into a tight little box. So here's some information on this particular build, how much laminate, how thick they are. You look at the different zones of the actual thickness in the areas, and then our impedance constraints and our target line widths. And then we use these numbers out on the floor to accurately hit your impedance numbers. So, this particular one is a little bit different. It's a bonded flex, laid out similar, but what makes it different is the customer is going for a high-speed circuit on the layer 1 and 2. So we're using Rogers material in combination with the flex and the typical FR4 base at the bottom, and they'll use this for RF signals and things of that nature that'll be on one side of the board. So that's pretty common nowadays. That's a picture of the board where the top side was
the high speed
with the high speed material.
Yeah, and for us, we have customers asking a lot about the high speed, with the all the new technology today and the need to push the limits of the 5G.
Yeah.
So this is an example. There's a lot of information out there talking about the comparison between the AP, or for example, DuPont adhesiveless AP product versus the Rogers, and then the new TK, or not the new, but the DuPont TK material. That's something that we're seeing a lot of questions today about that. So that's something that we can definitely recommend and explore more with our customers. In terms of the basic flex materials, we're using the DuPont model of LF, which we talked about, and some of the operating temperature, or lamination, the DKDF ratios there, and quotients, and then the FR. You want to explain?
Well, the FR material is a material that uses a different epoxy bonding, which is UL. You can make a UL product and put your logo on it. The LF material is not. So that's a big difference there. So we use that pretty regularly, especially in the medical products. They use a lot of the FR materials. Mm-hmm. The next one down, AP, is basically the adhesiveless material. So that can be built in with the FR cover lays and marked as a UL compliant material. And then the very bottom one is the TK, which is a Teflon-based bond, and very high temp, and it does a bit of a price driver, but you can see the DK and DF is pretty good on that. So in the right situations, the right builds, that's the material that the people will go for that need that performance. But it does drive up the cost a little bit more on that, just because the materials are quite a bit more.
Yeah, so the price between an LF, a typical LF clad, to an AP, we're seeing that probably the AP is about, not quite double, but maybe 50% more to the AP. And then from an AP to the TK, from the AP to the TK, it's about typically a 15 to 20% increase, depending on the actual makeup of it. So, of course, the lowest is the LF in terms of the cost per square inch, and the highest would be the TK.
Hey, Scott and Bob, I'm sorry to interrupt, but there are a couple questions. If you guys want to look in under the question tab, if you can see that, or I could read them directly to you.
Where's the questions tab? Oh, sorry. Here. Okay. Questions.
Just click on it.
Oh, here we go. Do you see that, Bob?
Are you able to mount a bare die or a flexible encapsulated IC direct on the PCB?
Not rigid flex. Are you able to mount a bare die? I don't know what that.
Well, that's the die set for the ball grid.
Oh, okay.
Yeah, we don't do that. Some assemblers will do that.
Well,
yeah, as far as that, ourselves, we don't mount the dies on, but I know there's boards we build that have the ball grids. They reinforce the backside, and they're definitely using flex and flex multilayers on that. But typically, you'll see it in the rigid areas.
Let's see here. I think we're having a problem with the.
The first one there says, I can read it to you guys. It says, what's the package size and the pin limit for mounting things like BGAs directly onto the flex substrates, like not onto the rigid flex, but the actual flex.
Package size.
That would be the pitch, right?
Yeah.
Yeah, I would have to verify that. I'm not sure how small we go down to. Basically a 2 millimeter, right? 0.2. But I know, yeah.
I guess we don't have. Let me see if we got that here. Package size limit.
Yeah. We can get that information to him.
Okay, we can get back to him on that.
Yeah, we'll get back to him on that, but we can get that.
Yeah, great.
Can't see that.
And then there's another question about currently, what are the maximum layers that you support with flex circuits?
We have, a few products up in the 7 and 8 layers constantly we're building. We went as high as 12, I think, recently.
The challenge is once you get that thick, it becomes very inflexible.
Yeah, the areas, what people do sometimes, it'll be removing layers that are unneeded, so it basically becomes a selective bend areas, if that makes sense. Well, they'll remove certain layers in certain areas to make it more flexible, even though the entire stack up is flexible.
Yeah.
So it has some Z-axis issues when you start going that high, depending on how you assemble it. You have to worry about getting the whole separation and stuff if you build too big of a flex, and then you have to use a lot of copper weight to try and keep everything tight together.
Yeah. So if we're working on a project right now where we're separating the inner flex layers, and let's just say if it was a 9-layer flex, then it's 3, 3, 3. So you've got 3 flex layers that are 3 layers each, for example, and that helps the bend radius. So that does help some of the flexibility. But just by nature, when you get to an 8 to 10 layer flex, it's very becomes more rigid. Yeah. And so it kind of defeats the entire purpose of the flex circuit. So
typically you would see that where they would be more forming it, or going around some type of a cylinder. They'll warm it, but it isn't what you would consider a bendable product that where they'll put a 90 or a 180 degree bend on it. They might be only putting a 10 degree or a 5 degree bend to form to fit.
Okay. Lisa, were there any other questions? We're trying to.
There is one more question. If you want to just go ahead and answer it now, or the question is, what's the maximum temperature that flex circuits can be exposed to in an SMT oven, and is there a suggested profile?
Well, that was the ones they just did the assembly on, right? The 260C, right? The profile we just did with we had just run a product through, and they typically are around 260C, I want to say, and it does take flex is very sensitive to assembly, heat rise and expansion. So the main thing is you need to do a lot of baking. The assemblers we work with, they pre-bake for a lot of time, and then they use probably a 10-zone oven so they can increase very consistently up to the actual flow point, and then cool it down. We have some literature on that too. We could forward that along. We provide with a lot of our customers with solder leveling and hand soldering versus the SMT assembly and flex versus rigid flex. But the main thing we find is getting the moisture out of the board and then using a very easy curve, I guess to say, to get to temperature. If you rise too fast, you'll definitely get separation on flex if it gets too hot too fast.
Well, good. And again, if there's any more questions, we would like to thank all of you for joining us on Flex Circuits. It was just a, really just brief overview on flex and rigid flex. There's probably thousands of more topics to consider on the flex circuit. But if you have any questions, please feel to email Bob, Scott, or Victor at these addresses, and we'd be more than happy to answer your specific questions. And
or they can come visit.
Yeah, come visit us here in Southern California anytime.
Yeah.